My name is Joshua Roy, and I'm a finally undergrad student. Dr. Chandrasekhar Vaddi. He is a scientist at the Defense Research Organization of India. Our paper is titled Impact of Pre-Processing on the Performance of Text-Independent Speaker Recognition System. I have to go fast because of 10 minutes. Speaker recognition system is basically biometric verification system, just like fingerprint. We use speech to verify people. There are two categories of speaker recognition system: text independent speaker recognition system. I can speak any random words and it can determine whether I am who I claim to be. Text dependent means it dependent on the text. The text is already predetermined and we have to speak the same text. There are two processes that happens in the speaker recognition system: training and testing. Training, first you take the speech signal, you extract some unique features from the speech signal, and then you model it. So for each speakers we have to create models. Testing, you get a signal, you don't know the speaker, you extract the unique features, you model it, then you see which of the speaker models does this particular model which you got most correlate with. That is how you find the speaker recognition system works. How to find unique features? Basically, unique features arises because of temporal and spectral properties of the speech. Temporal means speech time domain, spectral means frequency domain, and the spectrogram, that is this curve, captures this temporal and spectral properties because x-axis is time, y-axis is frequency. And when I tell two people to say the same phrase, suppose mouse, when I ask two people to repeat mouse, and I take the spectrogram of these two people, it will always be different. It will be very different, and that's the whole basis on how we find unique features. How to find unique features mathematically? Basically, we take this time domain speech and we convert it to something known as the cepstral domain or the cepstral frequency. From the cepstral frequency signal can uniquely identify uniquely capture the features which we want, the temporal and the spectral features it can uniquely capture, and the coefficients that we get from that, like we take the amplitude at specific intervals, and that is known as the cepstral coefficient. So these are the feature. Mel-frequency cepstral coefficient is a way of capturing the coefficient. It's a non-linear scale. For the initial few frequency we capture a lot of coefficients, then we capture less, so it's done in a Mel scale. That's how it is done. Now we can capture any number of coefficients, and we consider the 13 coefficient MFCC. And basically what there is something known as frame blocking. Basically we don't take a 5-second speech signal and find 13 coefficients from it. We divide it into many frames, overlapping frames, and from each of this frame we take 13 coefficients. So we have multiple frames. From each frame we have 13 coefficients. Modeling is done basically, if I give you an n-dimensional space and I can draw infinite number of Gaussian curves in it or Gaussian function in it. What distinguishes one Gaussian curve from another Gaussian curve is basically three variables. That is known as weight, mean, and variance. These three variables determine a unique Gaussian curve. So in the same way, I can model speakers based on Gaussian curves. So if I assign this as speaker 1, this Gaussian curve, and if I assign this Gaussian curve as speaker 2, basically both will have two different means, two different variants, and two different weights. That's how we model. Vector quantization is also modeling. It models based on the centroid. So I take a n-dimensional space. By the way, this n which I'm talking is basically the 13. It is a MFCC. We have 13 MFCC features, so it is a 13-dimensional space, both in GMM and in VQ. Now, in the VQ, we have a 13-dimensional centroid for each speaker, and this centroid is the specific model for that speaker. And if I get a new speech, I take the centroid of the MFCC coefficients, and I will find the minimum distance from all the centroids, and the one with the minimum distance will be the speaker it correlates to mostly. Now noise comes because of various sources. Random noise, it reflects on the surface and bounces back, and that creates noise. Does it matter? Yes, it matters, because I'm giving from a paper. This is example of a spectrogram of a clean signal and a noisy signal. You can see the variation. Intuition of our work started to create a speaker recognition system for a defense communication truck. So in this truck we have a lot of noise coming. There's engine noise coming, there is radar equipment noise coming. We have to keep cooling machines to keep the radar below at some operating temperature, which is very low, and that noise is also coming. So in this we had to create a robust system which can work in this noise. So basically we use multiple speech enhancement technique. So I'll just discuss it fastly. I cannot go inside the max because I have 5 minutes left. Voice activity detection, it can detect in a given 5 minutes 5 second speech, basically all the 5 seconds I won't be speaking. There are particular interval I will be speaking, there are particular interval I won't be speaking. It can detect which part I spoke, which part I did not spoke. It considers two, and so that's how it works. I'm just moving forward. Spectral subtraction method, there are parts where I speak, there are parts where I don't speak. So I know that the parts where I don't, if I consider noise to be additive white noise, this noise is present all over the speech, whether I speak or whether I don't speak. So if I take the part where I speak, it has speech plus noise. And when I subtract from this part, the part where there is no speech, if I can subtract, basically we will get a speech signal or estimate of a speech signal. That's how this works. So the generic algorithm just does the subtraction directly in itself, but there is another algorithm using over subtraction. It basically gives a more approximate subtraction, and it considers the adjacent frames, and that's how it does. It gives us a more accurate result. Wiener filtering, we design an optimal filter such that if we give a noisy signal, that is a speech plus noise signal, it can determine the speech, what the speech would have been. It's an optimal filter design, and this is the equation of the filter. Spectral estimator works that in such a way that it considers a conditional probability, that is a posteriori SNR and a priori SNR, and based on that it can estimate the signal. It can estimate the clean signal in the frequency domain, and then we convert it to the time domain. I have to go fast. What kind of data we use? All the speech which we use were 3 to 5 seconds long, which is quite short actually. And we use various recording devices. We called up our friends, we asked them to record. We had to discard more than 50% of the speech which we recorded, primarily because of the reason that the devices which were used, they had inbuilt noise reduction algorithm. We wanted to find a robustness in presence of noise, and we had to consider the systems which had no inbuilt noise reduction system. We asked from friends from various parts of India. There were various accents: North Indian accent, Northeast Indian, and South Indian accent. And the environment was completely random. We did not choose clean signal. While all the literature work on this speaker recognition use clean signals, we considered random environment. Finally, we got 47 speech signals, and out of that, for each of the 47, we had three speech signals, in which two they uttered the same phrase, that is library access, and one was the name or some random utterance. So for Gaussian mixture model, basically we divided the number of 47 speakers into three sets: 11, 23, and 47, to test the scalability. We observed that we get 100% accuracy when we use a VAD, that is voice activity detection. SU means same utterance, DU means different utterance. We get 100, but it suffers from a big problem, that is scalability issue. None of the 47, when we consider a system with 47 speakers, none of them has 50% accuracy. Everything is below except for one, I think. So it had a big scalability issue. VQ, on the other hand, were giving very promising results. And the important thing to be noticed here is this is a generic VQ algorithm. No reduction, no enhancement algorithms used. It gave us, for same speech, it gave us 93% accuracy. But when we considered noise reduction algorithm, voice activity detection, we got a 97% accuracy, from 93 to 97, which is quite a big jump. And for a different utterance, that is some random words different from the one which we gave for training, from 82 it jumped to 87 for SSMO, that is using over subtraction. So this proves that using noise reduction we can improve the quality of the speaker recognition system in presence of noise. Now this is a result of a work which we haven't published. Now we are working on it. Basically what this tells is, most of the literature exists now in neural networks, but the biggest problem neural network suffers is that it requires a lot of training data. Without providing ample training data, you cannot use it. Basically they are considering 24 MFCC features, we consider 13. We have to train it at least with 10 samples. We only trained it with one sample. For neural network we have to train it with 10 samples, and we are only getting accuracy of 79%, 79 to 83%. And the required epochs, that is time required, was 10 minutes to train. In this case it was just few seconds in our GMM and BQ. So these are the advantage over neural network. But why people use neural network is, neural network has good scalability. But our case, for a truck, we did not need scalability. We needed maximum 50 people. Applications: post-COVID world, we need a contactless biometric verification system, because when we do contact, COVID we can spread. We can use in the hospitals, universities, libraries, defense application, which we did. And these are the, thank you.